we're at the point where we're going to start talking about how the most common way that the data is actually structured. So it's not going to be just a simple list like a Python list. There's a different type of data structure that's more efficient, especially for inserts, because that's a big problem that we saw earlier. So how are these indexes actually implemented? And the answer is the B+ and B- tree. And I've got this image up here. And what is that? Maybe, so I guess there's not really a good question about that, but it's a tree, you can tell. And we're going to talk about how this works in just a second. So a B tree is a generalization of the binary search tree. And what is the cost for inserting in a binary search, so say in a binary search tree? And I guess probably a lot of people already know this, but I guess we have a Q&A then. Login. The answer is login, or the depth of the tree, which is the same as login. Yep. So now we've already got a point. Okay, this is solving the problem of insert, or at least improving the problem of insert. It's still not the same as inserting into the table, because if you insert into the table, well, that's just big O of 1 because you just put it at the end. So a B tree, like a binary search tree, is balanced, but it's different in that each node can contain up to order n number of keys. So here, it looks like we could point out to 5 different places here. So we're going to call this a order 5 tree. And this is a balanced binary search tree, but one of the things that you will obviously see is that they're not all, it's not required that each node have the full order n number of keys. So you could have 1, 2, 3, 4, 5 keys, and it would still be considered balanced. And let's think about how these dots work. So this dot is going to be less than 7. Anything to the left is less than 7. Anything between 7 and 16 are going to be between 7 and 16, not including 7 and 16. And then anything to the right would be greater than 16. So now if I want to say, oh, I need to search for row 5, or so the value 5, right? I don't need to go through all 6, 8, 10 values. I just need to go, okay, well, it's less than 7. So now I go here and it's 5. So the space is big O of n that this takes up, because we're not, we're just storing the values here. We're not doing any sort of matrix or anything. It's just storing the values. Insert into a binary tree is big O of log of n, and it's the same with a B- tree. Search is log of n. And then maybe if anybody wants to say anything about it, what is the running time for sorting with a B tree? Okay. Well, with a list, it would be n log of n. But if you think of how we're approaching this, we're doing it depth first search. And how do you, so it's ordered by depth first. So we go 7, and that points to this list. So 1, 2, 5, 6, these are already in order. And then we go back up, and then we go down, 9, 12, and we go back up, we get to 16, and then we go to the right, 18 and 21. So That's just the same thing as iterating through depth first search. It's going to be login. No, sorry, not login. It's going to be in just to iterate through. So it's actually not in login. It's better than just searching. It's better than sorting an unprocessed list. It's just basically iterating through all the elements. And at most, you're going to hit the element twice. So here, like 7, we go to 7, 1, 2, 5, 6, then we go back to 7, 9, 12, and we go to 16, right? So at most you go twice. So it's not login, it's at most 2 in, but it's going to be, that's equivalent to big O of n. Right. And the same thing goes with delete. And that's something we didn't talk about with the rudimentary naive example that I gave. But delete has the same problem as insert if you just have a list, right? If you delete one element from a list, you have to rebuild the entire list. But with a binary search tree and a B tree as well, you don't have to delete the entire list. You can just delete a node, and it takes login time to do that. And at the same time, we get the same search speed and the same order speed that we saw with that big long list. So this is the benefit of a B tree or a B minus tree, is that the B minus tree will still give you the same time for searching and ordering. But in addition, it will improve the speed of inserting and deleting. So there's another extension of the B tree, and it's called a B plus tree. So if we go back here, I mentioned that when we're doing the ordering, we are going, we will have to basically iterate, or sorry, touch or visit, I should say, visit each value up to 2 times. And we'll start at 7, we'll say, okay, well, there's a left branch, so I need to go left. And here there's only 2 levels, so that's nice, whatever. Then we have to go 1, 2, 5, 6, then we go back up to 7, then 9, 12, then we go to 16. So at most 2 times. Then we have a B plus tree, which is an optimized B plus tree, B minus tree for ordering. So you often hear B plus minus tree because they're very similar and they're almost the same. It's just the B plus tree is optimized for ordering. So a B plus tree is the same thing as a B minus tree, except that it has an extra feature that only the leaf nodes contain pointers to the table, and they're connected through a linked list. So in this case, we've got this B plus tree. And it's the same idea where basically how you iterate through it. So if I want to sort this or order this, all I have to do is I look at, okay, 3, and I go left. I keep going left while I'm already at the base of the tree. So I know that 1 is the lowest value. And then in the actual data only lives at the leaf node level. So when I say actual data, this is like the actual pointer to the table. So here on the leaf level, it's these different leaves are connected by a linked list. So we can go directly just 1, 2, 3, 4, 5, 6, 7. We don't have to go back up like 3. We don't have to do a depth first search. All we do is we search for the lowest value, least value, and then we can once we're in the leaf node, we can just go traverse through the linked list. So what does this do for you? It's rapid in order traversal. And so the same thing could be if I wanted to start at 3, right? So I've got 3 and 5. Well, I would go to the middle value and okay, here's my actual value for 3. And then let's say I want to order between 3 and 6 or whatever. I go 3, 4, 5, 6, and I'm done. So it's very rapid in order traversal. There's a little bit more space that's required. So basically you're trading time complexity with space complexity. So there's a little bit more space that's required because we're storing this 3 value 2 times. Same thing with 5, we're storing it 2 times. And so it's a small increase in space complexity and a small decrease in time complexity, but it's still considered to have the same overall time complexities and space complexities. And so the same search ability and same everything else. Let me see if there's any new things here. Okay. All right. So the difference, these are basically the same things, except that a B plus tree is optimized for in order traversal. And so it's a little bit faster if you're ordering or sorting. And it takes up a little bit more space because we have to, some values that were used for branching off, they also need to be stored in the leaves. So that some values are stored twice. Whereas if we were to go back here, we to the B minus tree, the values are all stored once because the actual pointers to the data in the table are stored in the actual nodes themselves. Now we're going to talk about another type of index. And this index we're going to talk about is called the hash index. And it's very similar to any type of like a hash, basically a hash map, essentially. So this is by far this is less common than the B plus and B minus tree. So for like a lot of SQL databases and a lot of other databases, the default one, if you don't specify any specific type of index, the default is just B plus tree or B minus tree. So how are these B plus, B minus trees, how are these indexes implemented? Sorry, how is the hash index implemented? So there's a few steps. First, you compute the unique key hash value. And so these keys right here are going to be unique. I use names, which is probably not great because names aren't unique, but these 3 names happen to be unique. And so you hash the key using a hash function. And what a hash function is supposed to do is take an input value, apply a function to it, and then the output of the function should be a uniformly distributed value. So if I were to say hash John Smith and then hash Jon Smith, so just leave out an H, what I should end up with are 2 hash values that are not related to each other. So if the keys are, if what I start out with is related, like John and John Smith, very close values, I hash it, I should get 2 values that are not related or very not related to each other. So it will uniformly distribute the keys. And so what we do is we hash the values and then we do a modulus depending on the number of buckets. So here we have 15. So we do mod 15, we'll end up with 15 buckets. And then the keys will be distributed between the buckets. So it's very similar to hash set, hash map in Java, and all these other languages also use the same concept. But here we're using it for a database. Okay. So we map the hash value to a bucket. We apply the hash function. We map it to a bucket. And the bucket, mapping it to a bucket, we're just taking the modulus of the value and then putting it in a bucket. So the space complexity of that operation is big O of n. Insert is very cheap. So insert is big O of 1, because all you have to do is apply the hash function, put it in the bucket. And these buckets are going to be a uniform size. So assuming that we're able to randomly distribute the keys into the buckets, then the bucket is only going to be up to a constant value. So when we insert into that, well, we might have to rebuild the list inside the bucket, but it's only going to go up to like 3 or 5. All right, and then search is big O of 1, because to search, all we have to do is we have to take the hash value of the key that we search for, find the bucket it should belong to, and then see if it's in that bucket. And if it's in that bucket, then it will point to the memory location or the disk location of where the actual data is. Delete is also big O of 1, because to delete, we take the hash value, we delete it, and then we find the bucket it belongs to, and then we just delete it from the bucket. So far, it sounds really great, because space is good. Insert is same as if you're just inserting into the table, so it shouldn't slow down inserts. Search is really, really fast. It's faster than the B+ tree. Delete is also faster than the B+ minus tree. So far it sounds better, but the problem is sorting is no better than just sorting the raw values, because when you take a hash, when you use a hash function, it should randomly distribute the values. So there's no ordering in terms of alphabetical ordering, anything in terms of these buckets. It's totally randomly distributed, or ideally randomly distributed. So ordering is not going to help. One really important benefit of the hash functions that I want to point out is that when you hash a value, you're going to get a constant size. Two values. Let me just make sure that we. Okay. So when you hash a value, so you hash a key, you're going to get a constant size. So if you hash a paragraph, you're going to get a hash value that's the same size as if you hash, one of these names. And if we go back here to the here, do we necessarily want to create an index, or there's a cost to creating an index where, we're basically indexing a paragraph, because then we're going to store the values in each of these cells in a B+ minus tree, and that's going to take up a lot of extra space. But if you use a hash index instead, then you're going to be able to essentially compress the amount of data down to whatever the size of the hash value is. So for some types of data, that might be the only way that you can actually create an index, is to use the hash index, because it would be too costly to try to replicate that data. So that's potentially another benefit. Some more Q&A here, possibly. Okay. So I understand that the key is being hashed through a hash function. On how do we handle collisions here? Okay. Let's go back. We've got 2 questions to talk about. So how do we handle collisions here first? So let's say, a hash function is not perfect necessarily. It might be that you hash 2 different values, and you get the same hash value. So let's say I hash John Smith and Sandra D, and they end up with the same hash value. Well, when I take the modulus of that, they're going to end up in the same bucket. And so the same bucket, so we'll have 2 in the same bucket. So now when we check if Sandra D is in the table, let's say I want to see if Sandra D is in there, I take the hash value, I see that there are 2 values in the bucket. I have to iterate through the values until I find Sandra D in there. Now, this becomes a problem, especially if you have a large number of collisions and a large number of items in the bucket. Now, when you're taking the modulus of the hash value, you expect that there's going to be cases, and it's kind of intentional, that you're going to have multiple values in a bucket. So if there's a hash collision, it's kind of no different than just when you take the modulus, you're going to have some remainders that are the same. But if you get too many value, or let's say that the overall, let's say buckets 0 through 15, on average, they have 100 values. We're getting to a point where there's too many values per bucket. So what will happen, it'll be a one-time operation. The database system will expand the number of buckets. And so now instead of 15, you might have 100 or 200. And then it'll redistribute the values in the buckets. And then you'll only have on average like 3 values per bucket. So that's the idea. What happens if there are too many values per bucket? If it turns out that they're not uniformly distributed across buckets, then that's probably an issue with the hash function. I mean, no hash functions are going to be perfect, but if it turns out that you have 45 values in bucket 0 and 1 value in bucket 1 and 2 values in bucket 3, right? Then you have a problem with your hash function, and that's probably that's an issue with the database system, is not using the right type of hash function. I think that that's something that you're not really going to encounter, because they've already been tested for that.